In this video, we will be discussing binary numbers and Boolean algebra. Binary numbers give us a convenient way to express real-world phenomenon in the form of numbers, such as zeros and ones. And Boolean algebra gives us a mathematical framework to manipulate these zeros and ones to achieve a desired output. So let's dive in.
A digital system is a set of electronics, shown here as a black box, that takes some input bits, shown here on the left, and produces some output bits based on those input bits. This class is focused on what's inside the black box and how we develop the electronics to control the outputs. All of digital electronics is really based on binary numbers. Now we're all used to counting in decimal, in which case the number 203 is really represented in 3 different digits here. And so this is the 10 to the 0th digit, this is the 10 to the 1st digit, and 10 to the 2nd digit. So we have 3 times 10 to the 0 plus 0 times 10 to the 1st plus 2 times 10 squared. Binary follows the exact same logic, except we just replace the 10 with a 2. And so we could represent the same number as 128 plus 64 plus 8 plus 2 plus 1, which are all powers of 2. And we can write out all of these bits. So we have 2 to the 0, which is 1, 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. So now we just populate each one of these locations with either a 1 or a 0 based on whether or not that power of 2 is included in the sum above. So this is a 1, 1. We don't have a 2 squared or 4, so that goes 0. And then 2 to the 3rd, which is 8, gets a 1. And then there's no 16, there's no 32, but there is a 64 and a 128. So if we were to write the number 203 in binary, we would get 203 base 10 is equal to 1100 1011 in base 2. Now, binary is not the only digital code out there. There's actually a few others that are commonly used. You're all familiar with decimal integers. Binary coded decimal is a code in which 4 bits represent a single decimal digit. And this is used in displays where you need some dedicated bits for each individual display. Octal, which is based on powers of 8, is rarely used anymore, but what you really see more commonly is hexadecimal. Hexadecimal is based on powers of 16. So the same logic can be used to make a hexadecimal number. So here we can see that 203 in base 10 is equal to 12 times 16 plus 11 times 1, which then is represented by CB. There's actually another way to get to hexadecimal, and that's going through binary. So if you remember, 203 base 10 is equal to 1100 1011 in base 2. And the shorthand route from binary to hexadecimal is to split this up into groups of 4 bits. Then each of those 4 bits can be assigned a single hexadecimal number. And so in this case, 1011 is equal to B, and 1100 is equal to C. So now that we have a way of representing numbers in digital systems, we need a way to manipulate them. And that's where logic and Boolean algebra come in. In essence, in a logical statement, A is either true or false. And this correlates in electronics as either a high or a low voltage. The simplest logic manipulation is the NOT operation. And this is denoted by any of these notations right here, although the bar over the character and the apostrophe are the most common, and those are the ones we're going to be using in this class. Basically, the NOT operation just inverts the logic value, so it makes a true become false and a false become true. When we translate this idea to circuits, the NOT operation makes low voltage become high voltage and vice versa. Another common operation is the AND operation. We can use any of these notations to denote the AND operation. In this class, we'll either use the dot or just the multiplication by putting the 2 terms next to each other. The output of an AND operation is only true if both A and B are true. Speaking in terms of circuits, this means that an AND gate will only put out a high voltage if both of the inputs also have a high voltage. Finally, the OR operation. Either of these notations work, but in this class we'll just be using the plus sign in order to denote the OR operation. Now the OR operation is true if either A or B is true, and they both can be true as well. One final thing to note is that even though we're using some common mathematical symbols here like times and plus, we really aren't actually doing times and plus operations. So it's important to keep this clear in your mind that these are really logical operations and not arithmetic. Now that we have basic logic operations that we can use to manipulate inputs and outputs, it's important to have a concrete mathematical framework. And this is where Boolean algebra comes in. At its heart, Boolean algebra is a set of axioms that describe how the AND, OR, and NOT operations work together. Here's a list of the axioms, and if you look closely, it looks a lot like the ordinary algebra that we use every day. On this slide, all the axioms in black are exactly like what you would expect for normal algebra. The red ones, however, are a little bit different. Take, for example, A or 1 equals 1. There's clearly no analog to that axiom in our traditional algebra. In this class, you will learn how to use these axioms to simplify logic expressions and hopefully make them a little bit easier to implement with electronics. An important concept in Boolean algebra is duality. What duality says is that if you swap 0 and 1 and the AND and OR operations in any Boolean expression, you get another valid expression. Now it's important to note that this is not the same or an equivalent expression. So let's take a look at a couple of these axioms and see how duality applies. So for example, if you look at the identity axiom, here we have A and 1 equals A. Well, if we swap AND for OR and 1 for 0, we get A or 0 equals A. For one more example, A and A complement equals 0. A or A complement equals 1. And then for the cumulative, associative, and distributive properties, all you have to do is just simply swap out the AND and the ORs and you still get a valid expression. One final and very important aspect of Boolean algebra is De Morgan's laws. De Morgan's laws are essentially a way to distribute a NOT operation across an AND or an OR operation. So for example, if we take the NOT of A and B, De Morgan's law states that this becomes A naught or B naught. And the converse is also true. If we take the NOT of A or B, this becomes A naught and B naught. So when we distribute the NOT operation through, we end up having to swap all ANDs to ORs and all ORs to ANDs. This is a very useful relationship when it comes to simplifying logic equations. Overall, Boolean algebra and the axioms and De Morgan's laws really form the basis for modern electronics as we know it. They provide a reliable framework to perform a wide variety of operations.